Hello, my darlings. So far up to now, we have always integrated what's called a proper integral, okay? An integral expression of the form, the integral from a to b of f of x dx, is considered a proper integral if the limits and the function are bounded. Proper integrals are always well defined, which means the limit converges, and that is the function is defined and bounded on the closed interval from a to b. The limits of integration are finite. That means they are numbers, okay? It's the integral from a number to a number of f of x dx. And the function has only finitely many discontinuities on the interval. For instance, if we have a function that's discontinuous like this, okay, let's say we're going from a to b and there's this discontinuity at c, we would break the integral up into two integrals and then be able to evaluate it. But if you have more than a finite number where you can count them, number of discontinuities, then you can't do that. So that's what makes a proper integral. Today, we're going to look at what happens when those conditions are not met, when integrals are considered improper. That happens if one of two things occur when defining the definite integral from a to b of f of x dx on the closed interval from a to b. Either one of the endpoints a or b is infinity, which means you don't have a closed interval, or the region defined by f of x has an infinite discontinuity on the closed interval from a to b. Now remember, an infinite discontinuity means there's a vertical asymptote. Let's see what happens. So first thing we're going to do is we're going to pull out our TI-Nspire and we're going to graph the function y equals 1 over x squared. So we're going to put in a graph page. We're going to put in our functions. So we're going to control division for our fraction template, 1 over x squared, and hit enter. Okay, and I do believe if I look at our little graph that I gave you, we're only really looking at this part of the function, and we just need a quick sketch. So here's our function y equals 1 over x squared from 1, and then as the x is increased without bound. And that shaded area that I shaded in green, that's the area under the curve. What we want to find is what is a from 1 to infinity. That's the area under the curve from 1 and going as x heads to infinity. Now, infinity is not a number, so x is increasing without bound. Is the area unbounded then? Or can we actually compute the actual area? That's the question. So if we think about the area from 1 to 10, that would be the integral from 1 to 10 of 1 over x squared dx. And this is only true because 1 over x squared is greater than 0 for all our x's greater than or equal to 1, right? This area is above the x-axis, so the area is equal to the value of the integral. Now, the area from 1 to 50 would be the integral from 1 to 50 of 1 over x squared dx. The area from 1 to 100 would be the integral from 1 to 100 of 1 over x squared dx. And then the area from 1 to 500 would be the integral from 1 to 500 of 1 over x squared dx. Let's go grab our calculators and see what happens. So what's happening to this area? It seems to be approaching a limit of 1, right? Those area values are getting closer and closer to the number 1. Now, what does the integral from 1 to infinity of 1 over x squared dx mean? Well, from what we did before, we know in this case that it's the area from 1 to infinity under the curve, okay? But it's a limit of this area, and it's a matter of whether or not this limit exists. If it exists, then we'll be able to compute the area. If the limit doesn't exist, then we can't. So what we do is we actually find the limit as b heads to infinity of the integral from 1 to b of 1 over x squared dx. So we change the integral back to a proper definite integral, and then we take the limit of that as that upper limit gets large without bound. If that limit exists, then the integral converges to that number. If that limit doesn't exist, then we say the integral diverges. So let's take a look. Now, geometrically, using our calculator, we think the area is approaching 1. Let's see if we can now analytically work that out. We would take the integral from 1 to infinity of 1 over x squared dx, and that's going to become the limit as b heads to infinity of the integral from 1 to b of 1 over x squared dx. Now that is still the limit as b heads to infinity of, now remember, this 1 over x squared, that's really x to the negative 2, right? So if we take the antiderivative of that, that's x to the negative 1 divided by negative 1, such that x goes from 1 to b. So we still have this limit as b gets large without bound of, now if we substitute in the upper limit, we'll get negative 1 over b, minus, if we substitute in the lower limit, we're going to get negative 1 over 1. Now that minus a negative becomes plus a positive. So we are actually looking at here the limit as b approaches infinity of negative 1 over b plus 1. Now, as b gets large, that means that the denominator of this fraction is getting large, while the numerator stays 1. 1 over 10, 1 over 100, 1 over 1,000, 1 over 10,000. That fraction is going to approach 0. And the constant 1 is still going to be 1. And 0 plus 1 is 1. So the value of our integral is 1, just like we saw numerically. Let's look at another problem that seems very similar. We're going to consider the area under the curve y equals 1 over x. Now that's the rectangular hyperbola xy equals 1. So I know that's going to look something like this, but we're going to start it at 1, 1. Very much like what we had in the last picture, right? Seems like this is going to be familiar. But let's see what happens. Remember, again, for all the x's greater than or equal to 1, our y equals 1 over x is greater than 0. So we can say that the area under the curve from 1 to 10 is the integral from 1 to 10 of 1 over x dx. The area from 1 to 100 is the integral from 1 to 100 of 1 over x dx, and the area from 1 to 1,000 will be the integral from 1 to 1,000 of 1 over x dx. Let's see what our calculator says. I'm going to add a page just so I have a clean place to work. I'm going to go get my integral. We want to find the value of the integral from 1 tab to 10 tab. This time our function is 1 over x, and we're going to tab dx and press enter. We've got 2.302585. I'm going to arrow up. Let's change that upper limit from 10 to 100 and press enter. 4.60517. Okay. Let's tab up again. We'll copy that integral. Change the 100 to 1,000 and press enter. 6.907755. Their notes seem to be leveling off here, do they? Let's do one more, even though we didn't think we're going to. Let's make this up to, let's go from 1 to 10,000. 9.2103. All right, let's see what's going on. Well, these numbers are not very similar at all. They do not seem to be leveling off. They seem to be increasing. Let's take a look and see what happens when we look at it analytically. So this integral from 1 to infinity of 1 over x dx will be the limit as b approaches infinity or gets large without bound of the integral from 1 to b this time of 1 over x dx. So that's going to give us the limit as b approaches infinity of, now the antiderivative of 1 over x is the natural log of the absolute value of x, but I can drop my absolute value because I'm only dealing with x's that are greater than or equal to 1, and our x's are going from 1 to b. So now we're going to have the limit as b gets large without bound of, if we substitute in our upper limit, we have the natural log of b, minus, we substitute in our lower limit, the natural log of 1. Now, the natural log of 1, that's easy. This is 0. But the natural log of b, as b gets large, remember your natural log graph? This is 1. The graph comes just like this, right? And as our b's, which are x values, get large, this graph is also going to get large. The natural log of b is going to increase without bound. That means that this limit is increasing without bound. And that means our area diverges. We are not going to be able to find the area under that curve from 1 to infinity. It's not going to slow down. It's just going to keep accumulating. Okay, there we go. Let's look at another one. Now here's another problem where we have an integral from negative infinity to positive infinity of 1 over 1 plus x squared dx. First thing we're going to do, we're going to graph the function. We're going to add a graph page this time, and we're going to use our fraction template. We want 1 over 1 plus x squared, and hit enter. There's our function. Look at that. Okay, so we looked at our graph, and is there any symmetry? Actually, yes, there is. This graph is symmetric with respect to the y-axis. That makes this an even function, right? It also means that the pink area and the green area are the same. They have the same area, right? Which means we can take this entire integral from negative infinity to positive infinity and rewrite that as twice the integral from 0 to positive infinity of 1 over 1 plus x squared. I guess technically you could also do 2 times the integral from negative infinity to 0 of 1 over 1 plus x squared dx. Either one, they're going to be the same. Personally, I like positive infinity. So now let's algebraically see if we can't find the value of this integral. So we take the integral from negative infinity to infinity of dx over 1 plus x squared. That is, we just said, twice the integral from 0 to infinity of 1 over 1 plus x squared dx, which is 2 times, because 2 is a constant, I can factor that outside the limit as b heads to infinity. Okay, because we have to change that integral from 0 to b of 1 over 1 plus x squared dx. So I still have my 2. I have my limit as b approaches infinity. And my antiderivative of 1 over 1 plus x squared is tan inverse of x. And we're evaluating from 0 to b. So now we have 2 times the limit as b approaches infinity of, and we substitute in our upper limit, we'll have tan inverse of b minus tan inverse of our lower limit, 0. Now, if we think about this, the 0 is easier, I think, for most people. The angle whose tangent is 0 would be 0. Now here, we want the angle whose tangent is b. If you think about this tan inverse graph, remember it looks like this, and it has a horizontal asymptote here and a horizontal asymptote here. The limit as the x gets huge of this tan inverse, right, as the graph goes off to the right, this graph is leveling off to that asymptote, which has a height of pi over 2. So our tan inverse of b, as b gets large, is going to approach pi over 2. So that means this limit is going to become 2 times pi over 2 minus 0, which is going to give us pi. And there we go. That one has a value we can compute. So we can look at these improper integrals with infinite integration limits. So where the infinity is at a limit, there's 3 cases. If f is continuous on the interval, including a, but increasing without bounds, then we would take the limit as b heads to infinity and change this upper limit to a b. If f is continuous on the interval where we're including the b, so we're coming from negative infinity and we're headed to the value of b, so our integral looks like this. This time we change the negative infinity to an a, and we take the limit as a is approaching negative infinity. In the third case, where f is continuous on the open interval from negative infinity to infinity, we would have to break that into 2 separate integrals, and then each one of those gets computed using one of the above rules. Or, like we did in one of the other problems, if f of x is even, we could change that to twice the integral from 0 to infinity. Then we only have to deal with one limit, but it still got broken up into 2, but we realized the 2 values were the same. Now, some helpful hints when you're dealing with improper integrals. It is helpful to remember that it's really 2 problems. First, it's an integral problem, and then it's a limit problem. Sometimes, or some people always like to, but sometimes definitely, it's best to evaluate them separately. Sometimes it's nice to just deal with the integral first, then take that answer and put it back into the limit problem. It's up to you. Okay. The other thing is when you're breaking down your improper integrals, be sure that each integral is improper at only one place. And that one place should be either the lower limit of integration or the upper limit of integration. Okay. Now, the next example we have is going to illustrate another type of improper integral. So far, we've done it where we've had infinity at the limit. We also said it could be improper when the function has an infinite discontinuity, or there's a vertical asymptote either at one of the limits of integration or somewhere between the limits of integration. Let's see what happens now. All right, so the next thing we're going to do is we're going to grab our TI-Nspires and we're going to grab the function f of x equals 1 over the square root of x minus 2, and we're going to set our x window from 0 to 5. Okay, let's see what happens. So I'm going to put in another graph page. I'm also going to go to my menu, window zoom, window settings, because we only want the x's from 0, tab, to 5. And you know what? I'm just going to count by 1 so that I can tell where I am, and I'm going to click OK. Now I'm going to use my fraction template. 1 over, control, I would need the square root of x minus 2, and hit enter. Now notice I don't need these negative y values either. I also notice that my graph doesn't actually get to 0. It doesn't even get to 1, nor does it get to 2. That we actually have here, it looks to me like a vertical asymptote at x equals 2. And I can make this larger. Let's say 50. Oh, it definitely is. And you can tell that because the denominator when x is 2 would be 0. Non-canceling factor in the denominator gives you an infinite discontinuity. So now my question to you is, why would the integral from 2 to 5 be considered improper? Well, notice there's a vertical asymptote here, right? Because the value x equals 2 would make the denominator of our function 0. So the reason it's improper is because f of x has an infinite discontinuity, or a vertical asymptote, at x equals 2. So what I'd like to do next is I'm going to break this up into the two problems like I suggested before. We're going to solve the integral s of t equals the integral from t to 5 of 1 over the square root of x minus 2. Now in order to solve this integral, we're going to need a u substitution. So we're going to let u be x minus 2, which means that du dx is 1, so dx is du. Now we're also going to have to change the limits. If x is 5, then u is going to be 5 minus 2, or 3. If x is t, then u is going to be t minus 2. Now let's make the substitution. So we would have the integral from, instead of t, we're going to put t minus 2, and instead of 5, we're going to put 3, of 1 over the square root of, and that x minus 2 is our u, and our dx becomes du. Now that means we have the integral from t minus 2 to 3 of u to the negative 1/2 du. Now we're ready to take the antiderivative. Now the antiderivative, we add 1 to negative 1/2, we get 1. We want to divide by that exponent 1/2, but that's the same as multiplying by 2, which is easier. And we're going to evaluate this from t minus 2 to 3. So when we substitute in the 3, we're going to have 2 times the square root of 3 minus, now we're going to substitute in the t minus 2, we're going to have 2 square root of t minus 2. So this is s of t. Next step, we want to find this limit as t approaches 2 from the right of s of t. Now notice when we're coming at 2 from the right or from above, that's this piece of the function where the function is increasing without bound. Okay, that's why we're coming at 2 from the right, because that's the piece we're looking at. So this will give us the limit as t approaches 2 from the right of our 2 radical 3 minus 2 square root of t minus 2. Now if we take that limit, we're going to get 2 radical 3 minus 2 radical 0. And lo and behold, we now have the value of our improper integral. So now again, improper integrals with infinite discontinuities. The improper integral will converge if the limit exists. Otherwise, the improper integral diverges. If f is continuous on the interval where we include the a, but the vertical asymptote or the infinite discontinuity is at b, then we would do the limit as c. And it doesn't matter whether you choose the letter c, t, you can use whatever letter you want, okay? The limit as c approaches b from the left. Why? Because if we're on an interval from a to b, we're approaching b from the left of the integral from a to c of f of x dx. Now, if the vertical asymptote is at a, then we would change the integral from a to b of f of x dx to the limit as c approaches a from the right. Because again, if we're on this interval and we're coming towards a, we're coming from the right. Now, the third case is when f is continuous on the closed interval from a to b, except at some value c, in the open interval, so it's somewhere else. So say we're on the closed interval from 1 to 10, maybe the infinite discontinuity is at 2. Then we break the integral up into two integrals so that now our infinite discontinuity is at an upper limit and a lower limit, and then we go back to those first two cases. We'll look at that one in class together. Okay? Guys, have a wonderful day. See you soon. Bye.